Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at this fairly short but really key AS halogenoalkanes question. Within this question we've got a mechanism, and then we've also got a slightly different question to perhaps how it's been presented before, but thinking about the rate of nucleophilic substitution of different halogens within those halogenoalkanes. And this is something that comes up fairly often in terms of needing to understand why the rates of substitution are different. And we can talk about some of the ways that that's been asked. As I said, here it's been a little bit different, or it's been worded here rather a little bit differently to how it might have been in the past. But that is something that doesn't necessarily come up often, is often something that is forgotten by students. And if you haven't done this practical, then it might be something that you can't visualise as well as if you would have done the practical. Now we're starting off with a mechanism. So we're told that this question is about reactions of halogenoalkanes with hydroxide ions. And that's quite useful because then in the actual question, we're asked to outline the mechanism for the nucleophilic substitution reaction of 1-bromobutane with sodium hydroxide. Now, they've already told us that from the sodium hydroxide, we are focusing on the hydroxide ions, but of course, you will need to know your mechanisms well enough to know that that is what this question is asking you to use as a part of the mechanism. So, outline just means draw. I don't know why we use the word outline and not draw, but that's how it will be in all of the exam questions. You won't always get told which mechanism it is that we're thinking about. There's different ways they can present that. They might give you the name or formula structure of the reactant and the product, or they might give you some information, in this case, about the conditions under which this reaction occurs, because with hydroxide ions, we can also get elimination occurring if the sodium hydroxide has been dissolved into hot ethanol, as opposed to dissolved in water, which is sort of room temperature, warm-ish, not cold, but certainly not hot by any means. So the information that they've chosen to give us in this question is that it is nucleophilic substitution we're doing, and then we've got our the name of our starting halogenoalkane, and then we know that we're dealing with sodium hydroxide. And with nucleophilic substitution, there are different nucleophiles we can use. We've got the hydroxide ion, we've got the cyanide ion, and then we've got ammonia. So yeah, to know that that's the nucleophile that we're going to be using, that's also helpful. So first thing we need to do is draw the structure for 1-bromobutane. So butane, longest chain, 4 carbons. And then the bromine is on the first carbon. Now the first carbon can be at either end. I'm going to put it on this right hand side so that it's nice and easy to draw the mechanism. And then I need to pop my hydrogens into every other position on that carbon chain, like that. And with mechanisms, the bigger the better. The longer your bonds are, the less squished up all your atoms are, the easier it's going to be for you to clearly show where your curly arrows are starting from and pointing to, and all of that business. So yeah, if you can, try and maximise use of the space that you've been given. Now our hydroxide ion is our nucleophile, so it's OH minus. Now the negative charge belongs to the oxygen, and they can be quite picky with that. So rather than writing the charge at the end after the hydrogen, put it on top of the O. And then whenever we're thinking about the position of curly arrows in any mechanism, they always have to start from one of two places, a lone pair or a covalent bond. And that's because a curly arrow represents the movement of a pair of electrons. So we then need to get our lone pair drawn onto our oxygen atom like that. Now, when it comes to nucleophilic substitution, the curly arrows will always be in the same place. Now, a nucleophile is an electron paired donor, so the hydroxide ion is going to want to donate a pair of electrons to something, and then we're substituting. So the hydroxide ion is then going to take the place of something, which is going to be the bromine or whatever halogen atom you have. So for the nucleophile to donate a pair of electrons, it's going to want to be attracted, or it's going to be attracted to something that has either a positive charge or a partially positive charge. And it's this polar bond that gives us bromine a delta negative charge, carbon a delta positive charge. You would not need to show those partial charges to get marks in this mechanism. If you do want to put them on, that is fine. Just don't get them the wrong way around or you will be penalised. So the lone pair of electrons, curly arrow needs to start at the side of them, not from the top, not somewhere miles away from the lone pair, from the lone pair, and it's going to need to point to that carbon there because that is our delta positive carbon. So nice and clear, starting at my lone pair, going to my carbon. That's then going to form a bond between this carbon and this oxygen. And this is why this is substitution, because we can't then have that carbon bonded to 5 things. So we have to get rid of something so that the OH can take its place, which is the bromine atom. So the pair of electrons in the covalent bond will leave with the bromine. So the second curly arrow goes from the bond to the bromine or whatever halogen it is that you're substituting. And that's it for your 2 marks, 1 for each curly arrow. There is no need to draw the products because we can only get 1 product in nucleophilic substitution reactions. Again, if you draw the product and you get it wrong, then you would be penalised. If you draw it and you get it right, you don't get anything for doing that. The one time I might suggest drawing it perhaps in pencil is if you were then asked to name the product, because it can be helpful to have that visually. But yeah, so that's part A. Then we're going on to this second part where we're looking at the rate of nucleophilic substitution of halogen or alkanes with those hydroxide ions. So how quickly will those hydroxide ions swap places with the halogen? Now they've done that with 2 different halogens. They've used what we've just had a look at, 1-bromobutane, so bromine is our halogen. They've also used 1-iodobutane, so iodine, as our halogen. It says we've got identical concentrations of those and that they were reacted separately with sodium hydroxide solution under the same conditions. And what they're essentially trying to get at there is that there's no kind of difference in terms of temperature or anything that's going to affect the rate, like the concentration. The only thing that is going to give us different rates of nucleophilic substitution is the different halogen atoms in those 2 compounds. It then says the concentration of halide ions was monitored during each experiment. And that is what we then have in our graph on our y-axis. So over time, we are measuring the concentration of the halide ions. Now, thinking back to our mechanism in part A, once that substitution has occurred, the Br here will be leaving with an electron that it originally shared, but it will also be leaving with an extra electron and become Br minus. We can then add silver nitrate solution, because then the silver ions from the silver nitrate will react with the bromide ions to give us a precipitate. And it would be the same when we're using 1-iodobutane. The iodide ions that come off would react with the silver to give us silver iodide. And the silver bromide would give us a cream precipitate, and the silver iodide would be a yellow precipitate. And they have asked that previously. That links in with group 7 knowledge that you will need to have in terms of how can we see how quickly these things happen. And the experiment that I used to do with my students when I worked in a school was exactly this. We'd do the substitution, we'd add some silver nitrate into the test tube as well, and then we'd simply time how long it took for the precipitate to form. So this one we've got slightly more information because they've measured the concentration of halide ions over time, whereas in the experiment that I did with students, we just had one measurement, which was the time it took for the precipitate to form. we could still see that there was a difference in rates, as we can see here. So the continuous thick line is the reaction with 1 iodobutane, and then the dashed line is the reaction with 1 bromobutane. And for the final 2 marks of this question, we have to state how the graph shows that the rate of reaction of 1 iodobutane is faster than the rate of reaction of the 1 bromobutane, and then we have to state why the rates are different. So in terms of our graph skills, when we're thinking about how graphs show faster rates of reaction or slower rates of reaction, we are looking at one of 2 things. One, the steepness of the gradient at the start. 2, the point at which the kind of concentration of the final product, if we're measuring the concentration of product, when that levels out and stops changing. And we can see for the 1 iodobutane line on this particular graph, it's steeper at the beginning, and we also get to a point where we've made all of the 1 iodobutane at a time that is plotted on this graph, whereas the 1 bromobutane reaction is still going at 600 seconds. We should get to the same point because we've got identical concentrations of those 2 different solutions. So I personally like to think about the steepness of the curve, so we can see that in the first 100 seconds we have got more iodide ions that we've been able to measure than we have bromide ions at 100 seconds, and it's the same at any time period on the graph. So the graph shows the reaction with 1 iodobutane is faster because the curve is steeper. And then for your guys' benefit, I'm going to put greater concentration of I minus ions measured at any given time. And then in terms of why the rates are different, this can sometimes be kind of thought of in the context of, well, we've got differing polarities of the bonds between the carbons and the halogens. So is it a case of electronegativity plays a part in that more electronegative halogens would have a greater pull on that shared pair of electrons with the carbon? Does that make it easier for the halogen to leave? Or the other argument is that it's based on the strength of the bonds. So is it that some of the bonds are weaker, so take less energy to break? Some of them are stronger and take more energy to break. And based on data like this, we can see that it has to be linked to the latter of those 2. So the bond enthalpy, the strength of the carbon-iodine bond. It has to be easier to break that bond, and that is therefore why we get more iodide ions formed at any given time period than we do bromide ions. The carbon-bromine bond is stronger than the carbon-iodine bond, and the carbon-chlorine bond is then stronger again than the carbon-bromine bond and the carbon-iodine bond. So the weaker the bond, the quicker we get rate of nucleophilic substitution. If it was down to electronegativity, the trend would be the other way around, because the most polar bond would be carbon and chlorine, so we would expect to then find that the chloride ions would be measured at greater concentrations, or in this comparison, it would then be the bromide ions that were measured at a higher concentration. That's not what we can see in the data. So it has to come down to bond enthalpy. And we know the carbon-iodine bond is weakest because if a carbon and iodine are sharing a pair of electrons, the electrons in that shared pair are going to be quite far away from the iodine's nucleus, because iodine is the biggest of the halogens. So the iodine will have less attraction to the shared pair then the bromine will have to its shared pair and the chlorine will have to its shared pair because of the size of the halogens. So the reason why the rates are different all comes down to bond enthalpies. So state why the rates are different. The rates differ because the carbon iodine bond is weaker than the carbon bromine bond, and that will be enough. It's always good to have that comparison in there. So the Ci bond is weaker than the CBr bond, not just that the Ci bond is weak, because that's not comparative for the two carbon to halogen bonds we're thinking about, but that would be sufficient. But if we have a weaker bond, then it's going to be easier to break that bond, and therefore there will be more halide ions being released. And I would say more of that if this question was worth more than 2 marks, but it isn't. So we do need to be aware of that. That's come up as a multiple choice question before, where it's asked you which would give you the greatest rate of substitution and why, and it's kind of been like in a table with 2 columns, and you've got to say pick which one would be fastest, and then pick the right reason why as well. Sometimes they've mentioned the silver nitrate and how that can be used to deduce that there's halide ions being substituted off. Most of the time it's getting you to think about this idea of bond enthalpy. But if you have a look at any other questions that feel similar and you want to send them over for me to have a look at, of course, please do. And if there's any questions specifically about this question, of course, again, please just ask. Thanks so much for watching, guys. I hope you found it helpful.